Hello and welcome to the next lecture of the course Machine Learning for Core Engineering Disciplines. And in the last several lectures we have laid a foundation in probability and statistics after having introduced the basic terms involved in machine learning, right. So today we will start out with the simplest possible machine learning model, which is a linear regression model, and this is a model that many of you may be familiar with, and we will use that familiarity to develop the concepts, but we will try to generalize it, right, into scenarios where there is not just one feature or one independent variable, but there can be many independent variables and features. So let us get started to see how linear regression works in practice. So the topic we are going to study is linear regression, and as many of you already know, this is the simplest possible machine learning model that one could develop. In fact, I mean linear regression was being done even before the field of machine learning sort of came into the picture. So in linear regression, right, we use a linear model to approximate an unknown function which depends on several variables, right, to predict a continuous target variable, right. And the meaning of a linear model, right, is that the model has exponent 1, right, in each of the features, right, and then you just sum over all the contributions and then you get the final prediction. Okay. So what we are interested in, our objective is to find the optimal parameters of such a model, right. So that is our objective, and to do that first we have to mathematically write down, right, this linear regression model. So how do we write it? So we can write it in this particular form: yi hat equals some beta naught plus some j going from 1 to p beta j x I j, right. So it is written in this particular form, right, and obviously we have to explain what these terms mean. So yi hat is the predicted value right of the target variable, okay. So hat denotes prediction, and you will ask what the subscript is. The subscript just refers to the data point number, right. So this is the predicted value of the target variable for the ith data point, okay. Obviously we have a data set with a number of data points, and this equation is being written for the ith data point, okay. Now what is xij? Xij is the value of the jth feature in the ith data point, right. So the index of the features is j, and this j, as you can see in this summation, j is going from 1 to p. So that makes p the total number of features in the model, right. So, P is the total number of features in the model. Okay. So, we have defined almost all the terms. There is one particular term that we have not yet defined, and that is beta, and this beta is referred to as the weight, right, and beta j is the weight of the jth feature in the model, right. So, now what is this beta naught? This beta naught is just some kind of an intercept, right, because you have to set the scale for your predictions, right. Your predicted value may be very large, so you may have an intercept in the model, right. So, this is the intercept, this is the prediction when the value of each of the features is 0, right. If all the features have value 0, then this summation term is not going to contribute, and the model prediction will solely come from the beta naught term. So, that is called the intercept. So, I hope this makes sense, and we have defined all the terms in this model. Y I hat is the predicted value of the target variable, beta naught is the intercept, beta j is the weight of the jth feature, and xij is the value of the jth feature in the I data point, and p is the total number of features in the model, right. So, the terminology is quite straightforward. Now, let us go and see how we can use this, right. And like I said, our objective is to find out the optimal set of parameters. Now, what are the parameters involved here? The parameters here are beta naught and all these beta j's, right. These are the parameters of the model, and our objective is to find what these parameters are. Now, the advantage of a linear model like this is that it is amenable to analysis using tools from linear algebra. Particularly, you can use things like matrices to represent these kind of equations, coupled linear equations. So, if you were to write this all these set of equations, remember there are usually n data points that we are considering. So, we should be able to write this in a matrix form. The left hand side, as you can see, is y I hat, and then you have a matrix right of the various features, and then you have the weight, right, the vector of weights beta. So, how you will write it is as follows. One equation can be written as follows: y I hat is beta naught plus some j going from 1 to p beta j x I j, and now we can write this in matrix form, right. So, there are n data points like I said. So, you can look at y1 hat, y2 hat, y3 hat all the way up to yn hat. So, these are all the predicted values, and then this will be equal to the matrix of features, right. Now, in some sense the common feature in all the data points is 1, right, because this beta naught is an intercept that is independent of the feature vector. So, the first column will be all 1s, right. So, that is the first feature, and then the rest of the features are x11, x12 and so on up to x1p, and this is x21, x22 up to x2p and so on and so forth. You can write the last row, which is xn1, xn2 up to xnp, right. So, this is the matrix of data, and finally, like I said, that has to be multiplied with the feature vector. So, sorry, the vector of optimal weights. So, that is beta 1, beta 2 and so on all the way up to beta p, right. So, you know how matrix multiplication works, right. That is the basis of all of linear algebra. It is done in a row by column type of form. You take this row and then you multiply it with this column here. So, that is how matrix vector multiplication takes place. So, you can see that y1 hat will be equal to 1 times beta naught plus x11 times beta 1, x12 times beta 2 all the way up to x1p times beta p, and similarly you get the expressions for y2 hat, y3 hat and so on, right. So that is how it looks in matrix form. So if you represented this as a vector y hat, this will be equal to the matrix of data x times the vector of the weights beta, right. So this is how it would look in matrix notation. Y hat is equal to x times beta, that is as simple as it looks in matrix notation. Okay. Now the thing is, we need to find out, like I said, this vector of optimal parameters, right. How do we do that? To do that, we have to minimize the error made by the model in predicting the data points. Now there is something called a loss function which you can define for a machine learning model, which quantifies the error made in our predictions, and in this particular case usually one works with the mean squared error. So we will define the mean squared error MSE, which is also called the residual sum of squares. Okay. So this is defined as MSE is a function of the parameters beta that is equal to 1 over n, that is the sum of squared errors here. So that is yi minus yi hat whole squared, sum over all values, and because it is a mean squared error, so you have to divide by n. If it was sum of squared errors SSE, this 1 by term would not be there, right. Now here, as you rightly may have guessed, this yi is the true value of the target variable in the ith data point, and this yi hat is, as we are already defined, the predicted value, right, of the target. Okay. Now if you wanted to write the full expression for yi hat, you can do that. So that becomes 1 over n sum I going from 1 to n yi minus beta naught plus sum j going from 1 to p beta j xij squared, right. So this is how the mean squared error would look, right, if you expanded it, right. Now to find the optimal set of parameters, right, you take this error MSE, which is a function of beta, and minimize it with respect to the set of parameters beta, and that will give you the optimal set of parameters, right. And you have to do this for every beta j that exists in the model, right. And obviously this only guarantees an extremum, right. This is for any extremum, right. To ensure a minimum, we need to verify that for that particular parameter. So let us say we are doing this with respect to the parameter beta j. So to ensure a minimum, you would have to check the second order derivative, right, and make sure that that is greater than 0 for a minimum, right. So this is what we want to do, and through this application of calculus we should be able to find what the optimal set of parameters are for the linear regression model. So let us see how we will do this, right. So like I said, you can either work with the mean squared error or the sum of squared errors. In what follows, I will simply work with the sum of squared errors, which I already told you is n times the mean squared error. Okay. So it turns out that the sum of squared errors, right, has a very convenient way to express it in matrix form, right. So it can be written as y minus x beta transpose times y minus x beta, right, and this follows from what we had done earlier here, right. So in matrix notation you saw that y hat was x beta. So what we are doing here essentially is y is the vector of true values and you are subtracting x beta from it. So that is the error, y minus x beta, and if you take y minus x beta transpose times y minus x beta, you will actually get the sum of squared errors, right. So it works out very nicely, right. So now if you expand this, what this becomes is y transpose minus x beta transpose times y minus x beta. So let us keep on writing it, and you know that x beta transpose, right, can be written as beta transpose x transpose. So if you keep on going ahead, this becomes y transpose y minus y transpose x beta minus beta transpose x transpose y plus beta transpose x transpose x beta, right. So this is what you get for the sum of squared errors as a function of the parameter vector beta. Okay. So I encourage you to work out these steps very carefully so that you convince yourself that this is exactly how it will be written. Okay, so let us go ahead. Now what I had told you earlier is that we will have to take the derivative of this sum of squared errors with respect to the parameter vector beta. Okay. So what we need to do is del SSE del beta, take that and set it to 0, and the nice thing about writing it in matrix form is that this equation takes a very simple form, right. So if you carry out these derivatives carefully using the rules of matrix and vector calculus, then you will see that the equation that follows is this. So del beta of SSE, and you can carry this out, comes out to be minus twice of x transpose y plus 2 times x transpose x beta. Okay. So that is what we have for del SSE del beta. Now we have to check the second order derivative, right, that is del squared SSE del beta squared, and clearly that is equal to 2 x transpose x. Now to understand, right, whether this leads to a local minimum or maximum, we have to understand a concept known as the positive definite nature of a matrix. This we will come to in one of the future lectures, but for now it suffices to say that this matrix x transpose x is typically a positive semi definite matrix, right, and that ensures a minimum in most cases. Right. So that is what we have in terms of the second order derivative test, right. Now going forward, what we need to do is we need to find out the optimal set of parameters beta hat, right. So for the optimal beta, denoted as beta hat, we will have to take this expression and set it to 0. So let us go ahead and do that. Your first order derivative is equal to 0. So minus 2 x transpose y plus 2 x transpose x beta hat will be equal to 0. So this means that 2 x transpose x beta hat equals 2 x transpose y, so that your beta hat becomes x transpose x inverse x transpose y. Okay. So what we have done is we have managed to derive an expression, right. So this is an expression for the optimal set of parameters, right. In other words, it is the parameters for the best fit linear model. Okay. And what we have derived here, right, we are assuming that the entries are real, right, and obviously sometimes you may want to predict complex entries. So all you have to remember is if x or y have complex entries, right, then you actually have to invoke the complex conjugate transpose, not just the transpose. So beta hat then becomes x Hermitian transpose x inverse x Hermitian transpose y, where x Hermitian transpose is basically x transpose complex conjugate, right, where this over bar is I am not denoting an average, this here is a complex conjugate, and this xh is also called the Hermitian transpose, which is essentially a complex conjugate transpose. Okay. So this particular quantity here, right, is very interesting, right, because usually, right, this particular quantity always exists, right, and it is called a Moore-Penrose inverse. So the matrix x plus, which is x Hermitian transpose x inverse xh is referred to as a pseudo inverse or a Moore-Penrose inverse, right, of the matrix X, and it is the generalization of the concept of an inverse to a rectangular matrix. right. Typically when you define the inverse of a matrix you have to work with a square matrix. However, in machine learning necessarily we work with rectangular matrices. Why? Because the number of variables, right, essentially is the number of features which is a lot more, and the number of data points is even more, right. So usually we work with data sets where there are a many number of data points and then much fewer number of features. So clearly we work with rectangular matrices, and this particular concept, the Moore-Penrose inverse, is very useful when working with such kind of matrices, right. So in fact, I mean, when in Matlab, right, you may have seen that if you have a matrix equation Ax equal to b, right, you can solve it in Matlab by writing x equal to a backslash b. So in a sense what is happening here is that the Moore-Penrose inverse of A is being calculated. So x is essentially being calculated as A Hermitian A inverse A Hermitian B. So that is what Matlab is doing, but it is denoted by this particular operator here, right. So I hope that sort of gives you an idea of how the linear algebra behind linear regression works, and with this particular equation, right, whether this one for real data or this one if you have complex data, you will be able to find the optimal set of parameters for your linear model, right. Now there are various metrics that are used to quantify the accuracy of the model. We already saw that one of them is the sum of squared error or the mean squared error, and you could also define the root mean squared error, which is the square root of the mean squared error. However, there is also another quantity known as the coefficient of determination r squared that is defined to quantify the accuracy in many cases. So let us look at how this r square is computed. So r square is called the coefficient of determination, okay, and it is a measure of the goodness of fit right. The closer the r square is to 1, the better your model is. So it is defined as 1 minus the residual sum of squares divided by the total sum of squares. So the term on the top, that is called the residual sum of squares, and the term in the denominator is called the total sum of squares, and this equation can be simplified as follows, right. Your residual sum of squares is sum I going from 1 to n, the difference between the true value and the predicted value, right. Essentially this is equal to the sum of squared errors SSE that we had worked with. So I remind you that this is the, for every data point that is the true value and this is the predicted value, okay, and the total sum of squares is defined as the sum over all the data points, the difference between the predicted value and the mean, right, the sample mean of the values. Okay. Now let us see how this quantity sort of changes, right, as we go from one model to a different model. So if you plug in this SS residual and SS total into the model, your R square will look like the following. The R square will become 1 minus sum I going from 1 to n yi minus yi hat whole squared divided by sum I going from 1 to n yi minus y bar whole square. Okay. Now what will happen for a perfect model? So for a perfect model, a model that is so good that it gives the right answer every time, your y I hat, the prediction will always be equal to the true value. So that means that this numerator here which I have highlighted will basically disappear, because y I hat equals y I. So your r square will become 1 minus 0, and that is basically 1. So for a perfect model, the r square will be equal to 1, right. And you can also show this on a so called parity plot. So a parity plot shows the predicted values versus the true values. So you can make a parity plot like this. So you have the predicted value here y hat, and then you have the true value here. So this is basically the predicted values, and on the horizontal axis these are the true values, right. And this is the line, right, that is y hat equal to y. So for a perfect model, all the data points will lie on this particular line, right. So this is for a perfect model, right. Now for realistic models, right, for imperfect models, obviously r square will be less than 1, and the lower it is to 1 will sort of tell you how worse the model is, right. So let us take an example when your r square is equal to 0, right. So when your y I hat is equal to y bar, then your r squared will be equal to 1 minus 1, right, because this term will be equal to 1, right, because your y I hat equals y bar, y I hat equals y bar. So that second term will be equal to 1, and you will get an r square of 0, right. So this happens when the model always predicts the mean value, right. So essentially the model could not do better than just predicting the mean value. So that is why the r square is equal to 0, right. And if you showed this on a parity plot, it would look like the following, obviously, right. Your y hat will be always equal to y bar. So this is this was r square equal to 1, this is r square equal to 0, your y hat equals y bar, and in this case your y hat was equal to y, okay. And in general the model can be anywhere between this, right. So as the model becomes better and better, it sort of tends towards the y equal to x line. And one thing to note is that r square can be negative also. Note that r square can be less than 0 for very inferior models, which are not at all able to explain the relationship between the data and the features, okay. So this brings us to the end of this particular lecture. In this lecture we developed sort of the math behind linear regression. We explained how we can derive a simple expression that relates the matrix of the data values and the vector of the true values to the vector of the optimal parameters in a linear regression model. We did that by writing an expression for the sum of squared errors and then minimizing it with respect to the parameter vector. We also saw how the coefficient of determination r square is defined, and then we saw for a perfect model r square equals 1, for inferior models r square can be very low, 0 or even negative, right. So I hope you got a feel for linear regression. We will of course go forward and also learn about confidence intervals for the parameters that we have defined, but all that will have to wait till the next class. Thank you, and I hope to see you there.